Hi guys, what's up? Are you good? I'm good myself. My name is Abram and today we're going to be doing physical sciences. I know that you love this show. This is Learn Extra, where you learn more and learn extra with us. Mr. Tinyuko, how are you doing?
I'm good. How are you, Abram?
I'm doing well, sir. I can't complain.
Yes.
Life is good.
Life is good indeed, and it's time for physical sciences, huh?
Of course. What are we doing?
Well, today, here I am, TK, coming to you with what we call chemical equilibrium and calculations. Actually, we'll be looking at chemical equilibrium and basically looking at calculations involved there. So if you have problems with your KC, if you have problems in finding moles, this is the time for you to sit back, listen, follow every step as I take you through this lesson because you're going to learn a lot.
Sharp, sir. I like it when you say you are TK, hey?
Yeah.
AKA. You're reminding me of Tinyuko, AKA TK.
Yes.
Right, guys? Yeah. We also want you to be part of this show by engaging with us. Send through your questions and your comments. Go to our Facebook page, which is facebook.com/LearnExtra, or follow us on Twitter @LearnExtra. We've got exciting things that are going to be happening during this show. We do have the notes provided for you guys. You can find them through this workbook. You can download. You can get an order by simply. You can put through your order by sending an email to sales@mindset.co.za. Mr. Tinyuko?
Yep.
Take over, sir.
Right. Let's begin with our lesson today. Like I said, we're talking chemical equilibrium. So I think by now you know exactly what this is all about, chemical equilibrium. It has to do, it's actually within the section on chemical change. And like I said, we're specifically going to talk more to calculations involved in chemical equilibrium. And you would know that when we talk chemical equilibrium and talk calculations, the main part of it will be the Kc expression. But of course, you can't get to Kc if you have not been to calculation of number of moles, calculations of concentrations. All those things will be here today. Now, let's have a look at what we have here. In the first place, let's define what chemical equilibrium is. Chemical equilibrium is a state, right? It's a state, a stage, a time in a reversible reaction. So we need to have a reversible reaction. A state in a reversible reaction when the rate, now that is key, when the rate of the forward reaction equals the rate of the reverse reaction. Now, what do we mean by rate? By now, you must have learned about rates of reactions. Now, when we talk of rate, we're talking about how fast something is taking place. So if it's a chemical reaction, in this case, we're looking at how fast that chemical reaction is proceeding, okay? How long does it take for number of moles of reactants to actually give us the product? So that gives us the rate. In other words, you can be looking at how much mass is formed of a product per time. When we talk of a rate, we're talking about something happening per unit time. Speed, for example, when you're driving a car, that is rate. If you say to somebody, I'm moving at 60 kilometers per hour, what it means is that every hour you would have covered a distance of 60 kilometers. So that's a rate. In this case, we're talking about how fast a chemical reaction takes place. Okay, so the time, if we have a reversible reaction, we know that things will be moving from left to right. Okay, so the reactant takes us to the products. But in a reversible reaction, the products as well decompose or disintegrate back to give us the reactants. So there will be time, if a reversible reaction is taking place, there would be time when, or a stage when how fast the reactants are giving us the products will be equal to how fast the products are giving us back the reactants. And at that state, we say that we have achieved or we have reached a state of chemical equilibrium. Chemical equilibrium can be reached when we have a closed system. If we have an open system, the matter and the heat, which is thermal energy, can enter and leave the system. Okay, so this is open. It's not a closed system. But for us to have a reversible reaction, to have a state of equilibrium reached, we need to have a closed system. In a closed system, only heat can leave, but we can't have matter lost. So we can't have matter leaving or coming into that particular situation because we have got a closed system. So in that case, we can have a state of chemical equilibrium being reached there. Reactions that take place in both the forward and reverse directions simultaneously, we call them reversible reactions, like I've said. And when we look later on, I'm going to give you or show you an example. We will observe or we'll see a process that is reversible shown in a chemical equation. And we make use of double arrows, okay? So arrows like that will say that it goes to the right and it also comes back to the left. Okay, that shows that the chemical equation is reversible. You would remember that if we have one arrow going forward, we are just saying that the reactants have reacted to give us the products, and nothing happens with the products to give us back the reactants. But once we have double arrows like that, showing the forward and the reverse, we're talking a reversible reaction. Observable microscopic or macroscopic changes stop, while microscopic changes, with something that we don't see, will continue to happen. In that case, we'll be having our reactants changing into giving us products, and of course the product will also be changing because it's a reversible reaction to give us what we started with, which are the reactants. When the rate, okay, now this is an emphasis of what I started with. When the rate of the forward reaction equals the rate of the reverse reaction, forward reaction equals the rate of the reverse reaction, we say that in a closed system, we say that a state of chemical equilibrium has been reached, or dynamic equilibrium has been reached. Okay, now to look at an example of what I was talking about, if we have a reversible reaction, say you've got A reacting with B to give you C and D. So A and B are your reactants, C and D are your products. If that chemical reaction is reversible, it would mean that as A reacts with B to give you C and D, so the top arrow here, this one, C and D are also reacting, being their products, to give us back our reactants, which is A and B. Now you would see here that I've got small a and small b in front of these letters, as well as small c and small d. This is just to say to you, this is a balanced equation. Remember balancing of equations? Yes. So that means that we've got a balanced equation. Now, because we have a balanced equation, the a there, the small a, will be representing a particular number. It could be 2, it could be 3, or whatsoever. Now, let's not lose focus of the fact that we're talking about a reversible reaction here. If we have a reversible reaction that has reached a state of chemical equilibrium, we can write down the expression for what we call the equilibrium constant for that chemical reaction. The equilibrium constant is symbolized Kc. Kc is called the equilibrium constant. In this case here, if I were to write the expression of Kc for this chemical equation that is in equilibrium, the Kc is always equals the concentration of products divided, I must have the big brackets there, divided by the concentration of reactants. Okay. Now, you would see here we've got 2 reactants, we've got 2 products. Now, This means that I would have the concentration of my products. My products in this case, it's C and D. So it will be product C. How many C's have I produced? I have produced C number of C's. So to the power, the balancing factor there. And the concentration of D. How many D's have I produced? The D's I produced are D number. So that balancing factor of D goes up there as my exponent, divided by the concentration of the product, concentration of A, and how many moles of A were there, A number of moles, times the concentration of B, and how many moles of B were there, B number of moles of B. So that's what I would have. So this is how I write down my Kc expression. But quick warning for you. When you are to write a Kc expression in the exam, in a test, you don't put that, because this is a general equation. I'm just using it to help you, okay, to help you understand this. So this is just a general equation from which I came up with a general expression for the Kc here. Now, you need to use, like I'm going to show you, use exactly what the equation is like, what has been given to you. Write it down like that. When they say write down the Kc expression for this reaction or chemical reaction in equilibrium, you have to look at that specific chemical equation and write it down properly. Now, when we move on from here, you would see that A, B, C, and D, okay, are substances that are involved in that reaction. If, and this is very critical, if these could be solids or what we call pure liquids, which would of course include your water, they must not be part of your Kc expression. So if there was water, if there was a solid there, I wouldn't put it up. And as we're going to see, because there shall be a lot of this today that I will be looking at, you would see how all these are omitted. When Kc has a high value, what does it mean? That means there would be proportionally more of the substance on the product side. In other words, you've got more products than you have your reactants. And we say that the equilibrium has shifted to the right if you've got more of the product and less of your reactants. In the same way, if you have the value of Kc having a very low value, usually less than 1, we would say that the equilibrium has shifted to the left. You have got more of the reactants than you have your products. Okay. Now, only temperature would always change the value of Kc. If any other factor like pressure, okay, and concentration are changed, those will never affect the value of Kc. But the change in temperature will affect the value of Kc, because this has to do with the type of reaction. Is it exothermic or endothermic? Okay, just to give you a clue there. Right, now, if pressure or concentration are changed, like I said, usually the equilibrium will adjust itself, will change when those changes happen. When you change the temperature by heating or cooling down systems, or change the pressure when we're talking gases, or change the concentrations of the substances, that will affect the state of chemical equilibrium. But from the three, only temperature will change the value of the Kc. The other two, concentration and pressure, would never change the value of Kc. So that is critical for you to note. Let's leave it at that point, and we're going to come back and unpack it more, do more examples, and show you how to use the Kc expression.
Thank you, Mr. TK. A big shout out to all the guys that are watching Refilwe, Moela, Olifant, Fortunate, and Khutato. Welcome, guys, and thank you for joining us. Send through your questions and your comments. We'll see you after this break. Welcome back, guys. If you just joined us now, I wonder where have you been, because most of you are late today. I'm not getting some of your tweets. I wonder what are you doing. But if you just joined us now, welcome. Get yourself the notes and go through what we're going through. Remember, we've got the notes on this workbook, of which you can get for only 139 Rand. All you need to do is to simply send an email to sales@mindset.co.za. Now, I've just seen a promo talking about accommodation. You as a matriculant could win yourself that free 1 year's accommodation for next year, because we know, TK, you would agree with me, at varsity, you know, as a matriculant, you need to think about the fees, you need to think about the textbook, you need to think about other things, and you don't want to worry about accommodation.
Yeah, no, definitely. I mean, accommodation is one critical thing. You need to know where you're going. When you leave your home and say, I'm going to varsity, where are you going to lay your head?
Of course. So we're giving you guys 1 year of free accommodation at any South Point accommodation next to a tertiary institution where you'd like to study. All you need to do is to simply fill in an entry form that I have for you on Facebook, and your name is on the draw, and all the best.
Yeah, thank you. Now let's come back to the lesson for today, continuing with this lesson on chemical equilibrium, and of course focusing on calculations. Let's have a look at this example here. Consider the following equilibrium reaction. You've got nitrogen reacting with hydrogen to give you ammonia, and thus is an exothermic reaction to the right because our delta H is less than 0, meaning that it is negative. Now, let's proceed and get more information on this. We are told that 9 moles of nitrogen and 15 moles of hydrogen are pumped into a 500 cubic centimeter container at room temperature. So we've got a volume here, volume of 500 cubic centimeters, right? And what is that? You need to actually convert that into liters, or what we call cubic decimeters. That will be 0.5, because you have to divide that by 1,000. Okay, so that is 0.5 cubic decimeters, right? The temperature of the gas mixture is now raised to 405 degrees Celsius, resulting in 8 moles of ammonia being present at equilibrium. So the temperature at which this state of equilibrium is reached is 405 degrees Celsius. Remember, I said only temperature can alter the Kc value. So it has reached equilibrium at that particular temperature. And the question is, calculate the Kc at that temperature, at the 405 degrees Celsius. Now I want to take you through this table. So watch carefully. In the first place, we have got the ratio. Ratio is what comes from the balanced chemical equation. So if you go back to the balanced chemical equation here, you would see that if you have got 1 mole of nitrogen, you would need 3 moles of hydrogen to produce 2 moles of ammonia. Those stoichiometric factors are the rule, if you like, in which these substances are combining to give you the product. So we call them the ratio. So it's 1:3:2. 1:3:2. So there is the ratio. 1 for nitrogen, 3 for hydrogen, 2 for ammonia. That is the ratio. It is from the chemical equation. The next part, it's what was there at the beginning. We are told that 9 moles of nitrogen are there at the beginning. So we put the 9 there. And we are told that 15 moles of hydrogen are there at the beginning. So all those information is given to us. But let me ask you a question. It is at the beginning, 9 moles of nitrogen, 15 moles of hydrogen. How many moles of NH3, ammonia, are we having? At that time, it is still at the beginning. We should be having, I hear some of you actually talking to it. If you think about it, at that point, there is nothing on ammonia. We don't have any ammonia at that time, so there is a 0. All right, 0 moles. But we are told that at equilibrium, so look at how you work on this table. At equilibrium, we have got 8 moles of ammonia. If I've got 8 moles of ammonia, what has happened for me to get from 0 to 8? Definitely the 8 moles of ammonia must have been formed during that chemical reaction. And therefore, I would say that 8 moles have been formed. And the change here, I would say that 8 moles have been formed. 8 moles have been formed. I can actually say that this is plus, so 0 plus 8 gives me 8. When I come to the others, you see now I know 8 moles have been formed. If 8 moles have been formed, or there is a change of 8 moles, I've got 8 for ammonia. Now I make use of my ratio. I make use of my ratio here to tell me how much of nitrogen has been used, how much of hydrogen has been used. And I'm saying has been used because they are reactants. So I would come here and say, all right, if I've got 8 that has been formed for ammonia, and the ratio is 1:2 for nitrogen and ammonia, 1 is half of 2. If I have formed 8, definitely half of 8 must have been used for nitrogen. And what is half of 8? Half of 8 is 4. So I've got 4 moles of nitrogen that has been used. If I have the 4 moles, now I have hydrogen to get. The ratio between nitrogen and hydrogen is that 1 mole of nitrogen will react with 3 moles of hydrogen. So 1:3. So 3 times what has been used for nitrogen will be the number of moles that has been used for hydrogen. So if 4 has been used for nitrogen, 3 times 4 should have been used for hydrogen. Let's see if that is the case. 3 times 4 is 12, so that's where we are. Moving on. At this point, I just need to get the difference, because in as much as I formed 8 moles of ammonia, my nitrogen and hydrogen are reactants. They must be used up. This tells me that 4 moles of nitrogen has been used up and 12 moles of hydrogen has been used up. So I can actually put the minuses here. This is minuses, and then for ammonia it's pluses. Now, when I do the calculation, 9 minus 4 should be what? Is a 5. 15 minus 12 should be what? 3. Okay? And therefore, these are my moles at equilibrium. These are my moles at equilibrium. And therefore, I will use this number of moles at equilibrium to find the concentrations of these substances at equilibrium. And remember that my volume is 0.5 cubic decimeters. So if my volume is 0.5 cubic decimeters and concentration is number of moles over volume, for nitrogen, I've got 5 moles. So it's 5 divided by 0.5. What will that be? That should be 10. So that is 10. Here it should be 3 divided by 0.5. 3 divided by 0.5, if you use your calculator, you'll see it is 6. So there it's 6. And then 8 divided by 0.5, you will see it's 16. So that is what I have. And therefore, I can calculate, I can find my Kc here. Kc for this chemical reaction here would be equal to, if you look at this chemical equation here, it will be the concentration of NH3, of course, to the power 2. There is the 2, all right? Divided by the concentration of nitrogen, okay? So N2 to the power 1. There is 1 there. And then times the concentration of H2, hydrogen, to the power 3. There is the 3 there. And then I can work this out. The concentrations have been calculated here. What is the concentration of NH3? It's 16. So it will be 16 all squared divided by concentration of N2, it's 10 to the power 1. Concentration of H2, it's 6 to the power 3. And you work that out. You can use a calculator, of course. Let's see that. Right, so you've got this, you've got 16 to the power 2 divided by 10 times 6 to the power 3. All right, so there we go. And let's see what do we get there. Right, so that gives us 0.12. So the value of this equilibrium constant here is 0.12. 0.12, and the equilibrium constant has got no unit of measurement. This is the only time, I believe, in your calculations that you'll come across where you are not expected to put in a unit of measurement. Kc has no unit of measurement. Okay, let's quickly go to another question here. William wants to determine the equilibrium constant for the decomposition of calcium carbonate. So calcium carbonate is CaCO3. He seals 2 grams of calcium carbonate in an evacuated 1.0 cubic decimeter metal flask and connects a pressure gauge to the flask. The flask is placed on an oven and heated to a temperature of 800 degrees Celsius at which equilibrium was then reached. And the equilibrium was reached according to this equation here. All right? The decomposition graph for calcium carbonate is shown below, all right? And then you will see it is the formation of carbon dioxide because they're talking pressure here versus time. All right, now, 1.1. How does the rate of the reverse reaction change from T0 to T1? You would see that at T0, the rate was at 0 moles per second, if you like. But it increased as you go up here, up to T1 here, from T0 to T1, so the rate increased. The rate increased. It increased from 0. From 0. To a higher value. Okay, we don't have the exact value, so I can just say to a higher value there. All right, now, 1.2. What is the reason for the horizontal line between T2 and T3? If you look at this graph here, T2 and T3, you've got a leveling up of that graph there. What does it mean? This is a reversible reaction. That would mean that a state of chemical equilibrium has been reached. Okay? State of chemical equilibrium has been reached. State of chemical equilibrium has been reached. So we have got a chemical equilibrium reached by this chemical equation here, or chemical reaction here. 1.3, you draw a sketch graph to show how the mass of calcium carbonate changes for the period of T0 to T3, so for the entire period, okay. In that case, you would see that if it is the mass of calcium carbonate, which is actually a decomposition process, this is calcium carbonate. That means that this thing is getting less and less as it forms calcium oxide and carbon dioxide. So what will be the graph here? So mass in grams of calcium carbonate and time in seconds. So that should be decreasing from some mass there. So it decreases, but definitely it would not touch the time axis, because at T, this is T, this must be T2, where it reaches, and that could be T3, where it reaches a state of chemical equilibrium. In other words, there is no more changes in the amount of calcium carbonate that is there. Okay. Next, we can then look at this question here that says, when equilibrium was reached, okay, at 800 degrees Celsius, the concentration of CO2 present in the flask was 1.4 by 10 to the power minus 2 mole per cubic decimeter. Calculate the equilibrium constant for this. Now, quickly, let's look at this chemical equation. You would see I've got calcium carbonate. It is a solid. I've got calcium oxide as part of the product, solid. I've got carbon dioxide. It is a gas, and let me put a tick there. Remember when we started, we said anything that is a solid, you cannot put it on your equilibrium expression. So it means that calcium carbonate cannot be part of it, calcium oxide cannot be part of it. The only substance in this case that would form part of my Kc expression is the carbon dioxide. So how do I do that? So Kc in this case would be equal to, remember, it's concentrations of products. So your product is CO2. Okay? And this is balanced as it is, so it's 1 there, this is to the power 1. I can't put any other thing. I can't have for calcium carbonate, I can't have that, or calcium oxide, I can't have it, it's a solid, neither would I have calcium carbonate. So Kc will be equal to that. I am to calculate for it. I'm told that the concentration of carbon dioxide at equilibrium is 1,4 by 10 to the power minus 2. So because that happens to be the only thing that I can put there, that happens to be your Kc expression. Hence, you were just asked to work for 2 marks there. Remember, with Kc, you're working for 7, 9, whatever. But here, you were just working for 2 marks. All right. The next question, let's start on it. It says the following equation represents a reversible reaction that has reached equilibrium at 470 degrees Celsius in a closed system. Now, again, it's that of nitrogen and hydrogen giving us ammonia. All right, delta H is less than 0, so the reaction to the right is exothermic. A change was then made to the NH3 in the equilibrium mixture at T2. A graph showing the effect of this change is drawn below. Okay, so it's drawn below. The graph is not drawn to scale, of course. And then the questions. What is the meaning of the horizontal lines between T1 and T2? So there is T1 and there is T2. You've got these horizontal lines here for H2, NH3, and N2. These horizontal lines, like we said earlier on, once you have those horizontal lines, they're telling you that this is a state of chemical equilibrium. State of chemical equilibrium. That's what they are telling you. Okay, so this is how you read these graphs. There shall be more on them as we move on and in other lessons to come. 2.2, explain how the change machine at T2 affected the concentrations of H2 and N2 gases. Now, if you look, you just read the graph, concentrations of H2 and N2. If you look at N2, it went up. If you look at H2, it also went up. So the concentrations of H2 and concentrations of N2 and H2 increased, okay? So these concentrations increased. They got to be more after that change. There shall be more of this type of questions, of course. Now, moving on, let's come to this one here. It says 1.5 mole of nitrogen and 2 moles of hydrogen were injected into a 0.5 cubic decimeter closed container. Okay, reaction vessel, and allowed to reach equilibrium at 470 degrees Celsius. When equilibrium was reached, you have got 1 mole of ammonia that is present. Calculate the equilibrium constant at 470, okay, showing all your calculations. We will definitely come back to this and work on it and try to close it nicely for you later on. Abram.
Thank you so much, TK. And there's some great comments and questions from the guys. I will take them after this break.
Okay, that's fine.
Welcome back, guys. Now, if you think you are a Bright Spark, enter the Be a Bright Spark competition and you could win yourself a cool Chevy Spark L, just like Dimakato, our very first winner. We've got 3 more cars to be given away, so you better enter right now. All you need to do to enter, it's simple. 1, you buy yourself the Safeways K53 manual. Or just download the Q100 app, which is available for only 59 Rand from the Samsung Galaxy App Store or the Google Play App Store. Thirdly, you just fill in the entry form. We've got the link for you on our Facebook page. Do check it out on facebook.com/LearnExtra. Now, TK, I've got some questions for you.
Yeah, boy, let's hear.
Okay. Right, the first one is from, okay, you'll excuse my,
Okay.
okay. Comment actually from Apiwe saying, I'm
Yeah.
tuned in, just keeping it low profile and learning. Welcome, Apiwe. Asanda Mnyandu says, Abraham, please ask, sir, when it comes to presenting the KC, will we be given H reactant and product state, or will we have to determine it? And if we're required to determine the state of a substance, how do we do it?
Okay, we'll deal with that. Any other?
Okay, another one, it's from I am Kmo Mukhoba. I don't understand how you got that 8 of ammonia in change.
Okay. No, that's fine.
Last one for now. Butsilo Tikane saying, could you please ask Diniko, how did he work out the change more 4 and 12 in example
Oh,
number 1?
yes. I think it's more or less the same question. The last 2 are more or less the same. And in the one that we're going to work on, we
Yes.
are going to see exactly how we arrive at that. We won't go back to the one that has 8 and whatever, but this one will actually show you or teach you where and how we get all those kind of things. And the one with the states, you are given, my dear, you don't have to think, they would always put those, that this is a solid, that's a liquid, that's a gas, that's aqueous solution. They will give it to you. Okay, good. Now, let's move on with this question here quickly. It says here, 1.5 mole of nitrogen and 2 moles of hydrogen were injected into this container. So let me stop there so that I take it slower for you. Let's come to the table. We've got nitrogen, we've got hydrogen there. I'm told at the beginning, 1.5 moles of nitrogen. So I would put it down here, and 2 moles of hydrogen. So I would say for nitrogen, I'm starting initially with 1.5. This is where I got it. I got it from the information given to me. The next one, hydrogen, it's a 2. Okay, then let's move on and read the question. Okay, it says here they were allowed to reach equilibrium at that temperature there, and the volume I'm also given because I'm going to find concentrations. Remember, volume is 0.5 cubic decimeters, the volume of the container in which all these substances are sealed together. Okay, cubic decimeters. Now, the question is, or as it proceeds, it says, when equilibrium is reached, so it's very important for you to read and understand what they are saying there. They are saying when equilibrium was reached, it was found that 1 mole of ammonia was present. So at equilibrium, how many moles of ammonia am I having? So I'll come to equilibrium. This is the equilibrium level. I'm told only 1 mole of ammonia was there at equilibrium. All this is information from the question. All that. Now let's work out what must have happened in that chemical equation or chemical reaction. If at equilibrium, okay, let's go to the beginning. I had 1.5 moles of nitrogen, 2 moles of hydrogen. How many moles of ammonia did I have at the beginning? It was still at the beginning, I had zilch, I had nothing. Okay. Now, I am told as the question or as the information proceeds that at equilibrium, 1 mole of of ammonia has been formed or is found at equilibrium, what must have happened? I started with 0. I'm now having 1. What must have happened with the change in the moles here? It would mean that for that change to have happened, I must have added 1 mole to my 0 number of moles that I started with for me to have 1 mole at equilibrium. Okay, so this is critical. Then, once I have found this out, I can then begin to use my molar ratio, this ratio here, to tell how much of nitrogen must have been used, how much of hydrogen must have been used. So if 1 mole has been formed for ammonia, has been the change, what must have been the change for nitrogen? Now, from the ratio, 1:2. So this means that if I formed 1, in other words, the nitrogen will always be half. 1 is half of 2. So nitrogen that has been used would be half the number of moles of ammonia that has been formed. So 1 mole has been formed. What is a half of 1 mole? It's 0.5 or 1/2. So that is half. So half must have been used. So this time, or this side, I will use a minus because this has been used. These are reactants. On ammonia, I'm saying plus because it is formed. It is a product. Okay, so this must have been used. Then how many moles of hydrogen must have been used? The ratio is, for nitrogen to hydrogen, 1:3. If 0.5 moles of nitrogen has been used, this one used must be 3 times the number of moles of nitrogen for hydrogen. Now, what is 3 times 0.5? 3 times 0.5 is 1.5. So that has been used for hydrogen. I'll put a minus there. The pluses and the minuses, I'm just putting them for convenience, for you to understand what is happening. So moving on, once I have dealt with this, I can then find my equilibrium moles. What are my equilibrium moles? I started with 1.5. 0.5 has been used for nitrogen. So what am I left with? I'm left with 1. Started with 1.5, 0.5 has been used. I started with 2 for hydrogen. 1.5 has been used, so 2 minus 1.5 is 0.5, okay? And therefore now, at this point here, I've got equilibrium moles. And it's equilibrium moles that I'm going to use to find my equilibrium concentrations, which is given by number of moles over volume. So this time here, remember the volume is 0.5 cubic decimeters. So I would have this as 1/0.5 cubic decimeters. So 1/0.5 will be what? Will be 2. And then 0.5 divided by 0.5 will be 1. Okay, so that is 1. Okay, let's confirm that. Yes, 0.5. And 1 divided by 0.5 again, that will be a 2. Okay, so that will be a 2 as well. 2 moles per cubic decimeter. Then I can find my Kc. Kc equals, okay? So that's the expression. Now, there is the equation. Remember? 1 mole is to 3 moles is to 2. So for nitrogen is to the power 1, for hydrogen is to the power 3, okay, and for ammonia is to the power 2. So concentration of ammonia, this is the equilibrium constant expression to the power 2, divided by concentration of N2 to the power 1 times the concentration of H2 to the power 3. And that would be equal to, what is the concentration of NH3? It is 2 to the power 2 divided by concentration of N2, it's 2 to the power 1. And concentration of H2 is this one here, is 1 to the power 3. And if you like, this is 4 over 2 times 1, which is 2. So the Kc here is a 2. Okay, so we can quickly work it out like that. Hopefully, it is answering the question, why, where did I get the 8? Can't remember the name there. Hope you're watching. Where did I get the 8? From the information given, and I could work out other things from that 8 there. All right, moving on, let's come to another example here. All right, this example here, again on ammonia. Okay, I'm using a lot of ammonia today, but let me use it because there's something it is bringing that I like. A fertilizer company produces ammonia on a large scale at a temperature of 450 degrees Celsius. The balanced equation for that is this down here. To meet and increase the demand for the fertilizer, the management of the company instructs their engineer to make the necessary adjustments to increase the yield of ammonia. So you want more ammonia to be formed. In a trial run, the engineer now injects 5 moles of nitrogen. You see now, 5 moles of nitrogen and 5 moles of hydrogen. All this information is from here into a 5 cubic decimeter sealed empty container. All right. Equilibrium is reached at that temperature. Upon analysis, the equilibrium mixture, he finds that the ammonia that is present is 20.4 grams. Calculate the value of the equilibrium constant. Now, there is no way that in calculating our Kc, we would use the mass, grams. So we have to change that. So in the first place, let me work on that. I need number of moles. This is the mass of ammonia at equilibrium. But I want the number of moles at equilibrium. So I will convert this, I'll work out the number of moles by using this formula here that you know very well. That it is number of moles found by the given mass divided by the molar mass of ammonia. So let me do this there so you see where it comes from. So you would see that the mass there is 20, the mass there, it's 20.4 grams. So, why is it doing this? Am I doing it too fast? Let me take it a bit slower now. 20.4 grams divided by the molar mass of ammonia. Molar mass of ammonia, you've got 14 for nitrogen, plus 3 into 1 for hydrogen. So what do you have? You have got 20.4 divided by 17. That is 14 plus 3. And that will give us the number of moles. And that will be what? Okay, 20.4 divided by 20.4 divided by 17 grams per mole. What do we get? We get 1.2 moles. So at equilibrium, what I have is 1.2 moles of ammonia. This is at equilibrium. Then I can use this to do my calculations. Okay, now firstly, remember what I said. You put things down, those things that are given to you. All right, so let's come to the things that have been given to us here. The engineer puts in 5 moles of nitrogen and 5 moles of hydrogen. So I come down here. For nitrogen, 5. That is at the beginning. For hydrogen, 5 at the beginning. For ammonia, if it is still at the beginning, it means I had nothing. All right. The change that was there, I need to check it out. But I'm told that 20.4 grams of ammonia is found at equilibrium, which is 1.2 moles. So at equilibrium, which is this level here, at equilibrium for ammonia, it's 1.2. Now, if I've got 1.2 there, it means there has been an addition to my 0 that I started with of 1,2. So that is the change for ammonia. And from there, I can use that through the ratio here to find out what happened to the others. Now, if this is 1,2, this one is always twice the number of moles of nitrogen. So number of moles of nitrogen are always half of what ammonia is. So half of that will be what? Okay, you divide that by 2. That will be what? 0,6. All right, so 0,6 moles of nitrogen has been used. So 0,6. All right, we write that down. Now, the number of moles of hydrogen that has been used will always be 3 times the number of moles of nitrogen. This is from the ratio. It's given to us, this ratio. Once you have balanced it, you have a given ratio like that. So this will be 3 times that of nitrogen. So what is 3 times 0,6? Okay, 3 times 0,6 should be 1,8. So that will be a minus. If you're not sure about that, you can go to your calculator and say 0,6 times 3, and you would see that it gives you that. All right. So that's how you work it out there. Then you work out the equilibrium moles by finding out the changes here. 5 minus 0,6 will be what? Will be 4,4. All right? And then 5 minus 1,8 will be what? Will be 3,2. All right, 3,2. Right. So that's what we have at equilibrium. Then we need to find the concentrations here, because for Kc, we need to work with concentrations. We need to work with concentrations. So concentration is number of moles over volume. All right. And what is our volume here? The volume is, let's go back to it. The volume is 5 cubic decimeters. So we're going to divide everything by 5 to find the concentration. Okay, so the concentration here will be 4,4 divided by 5 for nitrogen. So let's go there. 4,4 divided by 5. And what do we get? 4,4 divided by 5. We have 0,88. So this is 0,88. We come to hydrogen. So it's 3,2 divided by 5. Okay, so what do we get here? We get 0,64. And the last one, which is ammonia, is 1,2 divided by 5. 5 cubic decimeter is our volume. So what do we get? Getting 0,24. 0,24. I believe this is now becoming simpler for you to work out. Okay? Now, and once we have the concentrations there, we can then find the Kc expression. Unfortunately, we have run out of time. Please work it out on your own. You will see how to get your Kc there.
Thank you so much, sir. It's been a great show. You know, time is our enemy.
Wow.
We're always chasing after time.
Yeah.
Thank you so much. And thank you guys for tuning in. Really appreciate you guys. And thank you to the Department of Basic Education for making this show possible for all of us. We love you and have a great evening. Peace.